Hello and welcome to Game Theory. I'm Professor Naomi Utgoff of the United States Naval Academy, and in this video, we'll find and graph best response functions in matching pennies using mixed strategies. Last time, we found mixed strategy Nash equilibrium by finding what turns out to be only part of the best response functions we'll find in the current video. The goal of the first part of this video is to complete the equivalent of underlining best responses using mixed strategies. Here's the left-right steps in blue structure again. Steps 1 and 3 are the same steps from finding mixed strategy Nash equilibrium. However, steps 2 and 4 call for finding full best response functions, rather than the P and Q where the expectations are equal. First, we need to find player 1's expected payoffs from heads and tails, respectively. Done by the power of copy and paste from my other slide. We did this step in all of its gory detail in the previous video, and we won't do it again here. Now we need to determine player 1's best response function. Player 1's best response function maps player 2's strategy Q to a P that maximizes player 1's payoff. We see immediately that it is a piecewise function. If the expected payoff of heads is greater than the expected payoff of tails, player 1's best response is to play P equals 1, i.e. heads with probability 1. If the expected payoffs of heads and tails are equal, then all possible P are best responses. We denote all possible P by P in 0, 1 in the middle line. If the expected payoff of heads is less than the expected payoff of tails, player 1's best response is to play P equals 0, i.e. tails with probability 1. Since we want to express P as a function of Q, we should replace the inequalities in BR1 of Q with the expectations we found in step 1. Now let's do some algebra to tidy everything up. Let's give some intuition for this best response function. Player 1's goal is to find player 2, that is, to match her penny to player 2's penny. If Q is greater than 1/2, that is to say that player 2 usually plays heads, so player 1 is more likely to find player 2, i.e. match player 2's penny, by playing heads. If Q is less than 1/2, that is to say that player 2 usually plays tails, player 1 is more likely to match player 2's penny by playing tails. If Q is exactly 1/2, all of player 1's choices of P are equally good, so all choices of P are best responses. Regardless of her choice of P, player 1 matches with player 2 half the time and does not match the other half of the time. Now we need to find player 2's expected payoffs from heads and tails, respectively. Done again by the power of copy and paste. I'll be here when Wonder Woman goes on vacation. Now we need to determine player 2's best response function. Player 2's best response maps player 1's strategy P to a Q that maximizes player 2's payoff. We see immediately that it is a piecewise function. If the expected payoff of heads is greater than the expected payoff of tails, player 2's best response is to play Q equals 1, i.e. heads with probability 1. If the expected payoffs of heads and tails are equal, then all the possible Q are best responses. We denote all possible Q by Q in 0, 1 in the middle line. If the expected payoff of heads is less than the expected payoff of tails, player 2's best response is to play Q equals 0, i.e. tails with probability 1. Since we want to express Q as a function of P, we should replace the inequalities in BR2 of P with the expectations we found in step 3. Again, let's do some algebra to tidy everything up. Let's give some intuition for this best response function. Player 2's goal is to not match her penny to player 1's penny, i.e. to hide from player 1. If P is less than 1/2, that is to say that player 1 usually plays tails, player 2 is more likely to not match player 1's penny by playing heads. If P is greater than 1/2, that is to say player 1 usually plays heads, player 2 is more likely to not match player 1's penny by playing tails. If P is exactly 1/2, all of player 2's choices of Q are equally good, so all choices of Q are best responses. Regardless of her choice of Q, player 2 matches with player 1 half the time and does not match the other half of the time. We've previously visualized Nash equilibrium as the intersection of best response functions. we'll see that this visualization still obtains with mixed strategies. On the left, we have the matrix and the best response functions. We'll graph BR1 in red and BR2 in blue. I apologize in advance for the visually unfortunate nature of this graph. Economists the world over wince every time. When I took game theory, my professor winced too. When I teach it on the yard, you can see me wince. I am wincing now. BR2 maps P to Q, i.e. it maps numbers from the horizontal axis to the vertical axis. This direction is, I think, the one with which we're all more comfortable. It's certainly the one with which I'm more comfortable, so we'll start here. When P is less than 1/2, Q is equal to 1, which corresponds to the blue line segment. When P is equal to 1/2, we graph the entire interval of Q values from 0 to 1. When P is greater than 1/2, Q is equal to 0. Now we'll graph BR1 of Q. When Q is greater than 1/2, P is equal to 1. When Q is equal to 1/2, we graph the entire interval of P values from 0 to 1. When Q is greater than 1/2, P is equal to 0. This graph is very bothersome. I know. There is a problem on the homework that asks you to find and graph some mixed strategy best response functions, and that graph, I promise, has a different shape. At least this slide is the last one where we need to look at this graph. There is one intersection point, namely 1/2, 1/2, which is exactly the Nash equilibrium we found in the previous video. We can also see that 1/2, 1/2 is the only intersection point, so 1/2, 1/2 is the only Nash equilibrium of matching pennies. Thanks so much for watching this video about finding best response functions to mixed strategies. In the next video, we'll learn how to compute expected payoffs using mixed strategies.